Hello, welcome. Today we're talking about digital electronics, brilliant things. This is going to be a brief introduction onto logic gates. So what is digital electronics? Digital electronics is built on the foundation, the very foundation of logic gates, and this purely relies on logic gates. So you've probably seen these gates before probably in school, secondary school, maybe in your college classes, online perhaps. So they are fairly common. But before we get into that, I need to let you know that when we see these zeros and ones, this would mean binary. And in binary, there are only two situations. It's either on or off. What does this mean? It's either 1 or 0. It can't be 1.5, 1.7, or so on and so forth. It can either be 1 or 0. These logic gates are a type of amplifier, and more likely than not, they have one or more inputs with usually one output. So I believe inside there's like billions of transistors. So in our transistor video, I had said that your phone, for example, had millions of transistors. These logic gates are the same. Within these types of circuits, we'd be operating on two voltage levels, logic 1 and logic 0. And these type of gates can be described in different ways. It can be written, it can be in the form of a truth table, or in a Boolean algebra statement. In this case, we have the names of each of our gates and we have their truth table for them. So we have AND, OR, XOR, NAND, NOR, and XNOR, or exclusive NOR, exclusive OR. So for the AND gate, so A, B output, so this would be, for example, for A, B, and our output. This would be the same for all these gates going forward. I'm just going to start with the AND gate as an example. So if we had a logic 0 above A and B, our output would be 0. If we had a logic output of 0 at A and 1 at B, 0. 1 at A, 0 at B, 0. So then until we had 1 at A, 1 at B, then only then we get the output 1. So this is how you read the truth tables, and this is the same throughout, and this would be also the same if you had more inputs, but I will explain to you later on what if we had more inputs and how do we arrive at these values here. But for now, just keep this in mind. So here in this part, I should say, roll the Boolean for each of these gates, and as you could see, we have some symbols you may have not seen, but well, you've seen the addition, multiplication, but maybe this one you might have not seen. Or what do these lines indicate on top? Well, I'll briefly explain each one. So this dot symbol here is the symbol for the AND. Symbol indicates AND. Although in many cases this dot may be omitted, so you may just see it like that instead, so do not get confused with that. The plus indicates OR gates, so this is how you identify this is an OR gate being used. And this symbol here, this circle, the plus in it, means the exclusive OR, and we also have the exclusive NOR here, and I'll explain what is this NOR, NAND, so on. So if you haven't noticed already, if we take you can see these are all lined up with their corresponding here. So AND and NAND. If you see here, this is the complete opposite of what the AND gate is. So when we have a logic input of 0 and 0, get output 1. Logic 0 and 1, output is 1. Input of 1 and 0, we get output 1 again, but in comparison to the AND gate, when we get a logic of 1, 1, we get 0. So it's a complete inverse of it. And this is what this line here means. So this line, it means it's inverted. So all of our outputs will be inverted for the opposite. So this is how we identify this NAND gate. This applies across all these gates. This would be the NOR gate and the exclusive NOR gate. So, but there is one more gate I have not shown you, and it is the inverter. I believe that is the symbol, if my memory serves me correct. And its truth table is quite simple. As you can see, it only has one input, one output. And if you get a input here, your output 1, 0, 0, 1. It just takes the opposite of it, that's all. Quite simple. So these letters from the alphabet, A, B, C, you know, whatever you might see, this just indicates inputs. Do not be confused. And this output X here, X, Y, sometimes Q or P to label an output, they don't have any meaning. They're just to label an output. So sometimes in schematic diagrams you might see, let's do something here. So you might see, this is actually like a common one I've actually seen. So you might just have, let's see, let's go to there. So you have A, B, C. Of course this has 3 inputs now. They do a different truth table, but you get what I mean. And we'll have D, E, X. So D and E will be your outputs for these 2 AND gates here, and they will also be the 2 inputs for the OR gate here. So I've got the example circuit here, and this is a circuit I've just shown you before, but it could be any circuit. But anyway, let's get into this example. If a circuit was shown and you wish to analyze it and its operation, a truth table can be compiled using the following steps. So this is how we analyze our logic gate circuits, to know the outputs, the inputs, what's exactly going to do when we apply these different conditions. So firstly, a number of columns are written down which we will describe using 1s and 0s. So we've got 3 inputs here. So we've got A, B, and C. All conditions that occur at the input and in output are taken into account for the circuit. So this is what the truth table will be. So we've got our A, B, and C inputs, and they are filled with a binary count from 0, 0, 0. So our star will be 0, 0, 0 to 1, 1, 1. And this is a decimal count from 0 to 7, as if we were reading it from right to left. So when we do these kind of things, so it's 0, 0, 0, and so this would be the least significant bit, LSB. This would be the most significant bit, MSB. And I said this is a decimal count from 0 to 7. But how did I get the 7? Good question. How did I get the 7? When we're dealing with this like binary, each number corresponds to a certain power. So it goes 2 to power 0, 2 power 1, 2 power 2, you know, so on and so forth. If we had 1, 1, that would be 2 power 3, 2 power 4. So we only need to calculate if there's a 1 in here. So since we're calculating to 7, since we have 3 inputs, this means so what we do, if you do 2 power 0 times 1, we have 1. 2 power 1 times 1, 2 power 2 times 1, 4. So 4 plus 2 plus 1 equals 7. This is from binary to decimal. So 111 is decimal for 7. Easy. So since we have 3 inputs, this means we can only have a total of 8 combinations. How did I get 8? 3 inputs, 2 to the power 3, we get 8. 2 times 2 times 2, 2 times 2, 4, 4 times 2, 8. So we can only have 8 total combinations. And we're just gonna write down our possible combinations now. So here's our poorly written out table. We have all the possible combinations here for inputs from A to C, and as you can see we have 8 combinations now. So we have 2 outputs here. This means we need 2 more columns, D and E. And because we have an AND signal, so not AND signal, AND logic gate for both, so these are both AND gates, this would make it, our boolean would be AB and AC. So each of these columns are labeled with an output, and we need to use this boolean expression for each one to get our desired output. So we are going to quickly solve this. So this would be our output here for our outputs of D and E, and we've got one more step, and that is to find our output X. As you can see, I'm running out of space here, so I'm just going to move everything a bit. As you can see, we have our boolean over here. So we have our 2 inputs, A, B, because it's an AND gate, and we have A, C. There's also an AND gate, so their outputs are D and E respectively. And notice we have D plus E here because we have an OR gate over here. So do keep that in mind. It does change with every single gate, as we mentioned earlier. So what you would do is, then you would take the OR function, so the truth table I shown. So this is, so we're following this truth table 0, 0, 0, 0, 0, 1, because there is a logic 1 at one of our inputs, 1, 1, 1. Because when there's 2 both of logic 1, we get an output of 1. And that covers it for there. So this is how you would do your truth table here. This is a fully complete truth table of our circuit over here. So these truth tables are really valuable because any condition of the inputs, so whatever condition is, we can see what output it would generate, as well the outputs here. In comparison, so let's, for example, if we had a circuit in real life and we wanted to do some fault finding, we weren't too sure, we could refer back to this truth table and see, oh, maybe B over here has an input of 1 and it's produced an output of 1. This shouldn't be the case because the truth table says otherwise. So you can see its usefulness with that. So that's all I have for this video. I hope you've learned something. In the next video, we're going to be doing that amplifier project. We will be doing that. Just waiting for the PCBs to come in, and I'll be showing you guys on how to do that. But we'll take a look at more digital electronics. Alright, thank you so much. Take care.